guys, this is Mrs. Carnes, and in this video we're going to talk about particle motion, and specifically motion along the x-axis. So we're going to think about, if you think about the x-axis being a straight line, obviously, we're talking about a particle starting on here and just moving linearly or horizontally back and forth along this axis in some kind of motion, okay? So when we do that, x actually becomes the function. So you can think of position as being x of t. So x is the function and t is the variable, which is a little bit different. So the position equation gives you where the particle is located on the x-axis at any given time. So position gives you the position. Okay, and so then you can also look at the velocity, and we'll call that v of t. And obviously we already know that velocity is the derivative of position. And so it's going to tell you how fast and in what direction the particle is moving. It's similar to speed, but remember that speed is the absolute value of velocity, okay? And then acceleration, we'll call it a of t. And that is the derivative of velocity, or the second derivative of position. And so that's going to tell you how fast the velocity is changing. It'll also tell you if the velocity is increasing or decreasing. Okay? So those are the three relationships, and they're very important. So make sure you know who's the function, who's the derivative, who's the second derivative. All right, so then there's some other things that we just need to know. So if x of t represents the position of the particle along the x-axis at any given time, then the following statements are true. Initially means when the time, or t, equals 0. Initially should always be time 0. At the origin means where the position, or x of t, equals 0, okay? At rest means when the velocity equals 0. When you're at rest, you have no speed, right? You're not moving. So when is the velocity 0? If the velocity is positive, then the particle is going to be moving to the right, okay? So positive speed, positive velocity always gives you right motion. So then if the velocity of the particle is negative, the particle will be moving to the left, okay? So right is positive velocity, left is negative velocity. To find the average value over a time interval, remember average value, that's the same thing as slope. Divide the change in the position by the change in time, okay? So it's the slope of the position. Okay, so instantaneous velocity, remember instantaneous is another word for derivative. So it's the derivative of the position. So instantaneous velocity is the velocity at a single moment or an instant in time. That's why it's called instantaneous. Okay? If the acceleration is positive, so remember acceleration is the derivative of velocity, so if the derivative is positive, then the original function, which in this case would be velocity, is going to increase. And so if the acceleration is negative, then the velocity is decreasing. And in order for the particle to change directions, the velocity must change signs. You must go from a positive velocity to a negative or vice versa in order to change directions. Okay, so all of this is just really important information to know, things that you should just basically have memorized, and none of it is new. It's just specific to this example of particle motion. So now let's look at an example. So example 1 has a table. So they gave us a table, and you'll notice it's time and velocity, so it's always important that you read your table and make sure you know what this is a table of, okay? And so if we look at this table, the first question says, at time 0, is the particle moving to the right or the left? And so remember, you move right if the velocity is positive, and you move left if the velocity is negative. So if I look at time 0, the velocity is negative. So because the velocity is negative, I'm moving to the left. So I would say left because, it says justify your answer, the velocity at time 0 is negative. Okay. Is there a time during the time interval from 0 to 12 when the particle is at rest? So remember, the particle is going to be at rest when the velocity equals 0, okay? When it's not moving. So if you look at this table, is there anywhere where the velocity has to equal 0? So first of all, it's really important up here that it tells us that the velocity is differentiable. It also means it's continuous, okay? So that means no holes, jumps, or asymptotes. So if you look here, if I'm going to go from -3 to +2, and I have a continuous function, I'm going to have to hit 0 in between there. If we think about them on a graph, 0, -3 would be down here, 2, 2 would be up here. If I'm going to connect those, somehow I've got to hit 0. So the answer to that is yes. Between time 0 and time 2, the velocity changes signs. It goes from negative to positive. So the velocity must equal 0 somewhere in that interval. Between time 0 and time 2. So if you change from negative to positive or positive to negative, you're going to have to hit 0 somewhere in that interval. We don't know where, and we don't need to know where. It just wants to know, is it going to happen? Okay, so then it says, use the data from the table to find an approximation for v prime of t. Okay, so the only way you can approximate a derivative from a table is to use slope. So v prime of t would be approximately, so 10 is going to fall between 8 and 12. So I'm going to do the slope using 8 and 12. So I would do 5 minus 7 over 12 minus 8, which would give me -2 over 4, which is -1/2. So notice it says explain the meaning, show the computations, and indicate the unit of measure. So because velocity is being measured in meters per minute, the derivative of that would be measured in meters per minute squared. It's an acceleration. Anytime you have acceleration, time should be squared. Okay, so what is v prime of t? V prime of 10 is the acceleration at 10, okay? So it's the acceleration in meters per minute squared at time t, at time 10, so I keep saying t, 10. So we found the slope, we gave units, and we explained what it meant in terms of the motion, okay? And so because it's negative, you know that the velocity is going to be decreasing at 10 minutes. So then part D says, let A of t denote the acceleration. Is there a guaranteed time t equals c in the interval such that a of t equals 0? Okay, so this is actually going back to the intermediate value theorem. Because velocity, we know velocity is differentiable. That means the derivative exists and it has to be continuous. So because the velocity is differentiable, we know a of t is continuous, okay? And that's important because we can now use the intermediate value theorem if we have a continuous function, okay? So by IVT, if you remember, IVT says if you have two endpoints, you have to hit all the points in between them if you have a continuous function. So let's actually add this up here. Since the velocity goes from increasing to decreasing, and you can see that in the table, it starts out increasing until 8. Oop, can't see the table. It increases until time 8, and then from 8 to 12, it decreases. So since the velocity increases and then decreases, the acceleration is going to be positive and then negative. So the acceleration changes, let me change that, from positive to negative. And so by IVT, if you are going to change from positive to negative, you're going to have to hit 0 somewhere in the interval. So it's very similar to what we did in part B. So yes, somewhere the derivative is, or the acceleration is 0. Okay, so example 2, that was a table problem. Now we're going to look at a graph problem. And we're going to do a table, a graph, and a function to kind of get a taste of all of them. So if we look at this graph, here we have a graph again of the velocity. Always make sure you read your labels in feet per second from 0 to 9. So it says, at 4 seconds, is the particle moving to the right or the left? So if I look at t 4 seconds, 1, 2, 4 would be right here. So again, how do you tell if the particle is moving left or right? You look at the sign of the velocity. So the velocity at 4 seconds is positive, approximately positive 6. So because the velocity is positive, we're moving to the right. V of 4 is positive. Okay? Over what time interval is the particle moving to the left? So you're going to move to the left where the velocity is negative. So according to this graph, our velocity is going to be negative from 5 to 9. So 5 is actually 0, so I'm going to leave that as an open bracket, and then 9 is a negative number, so I'm going to close it. So I'm 0 from 5 to 9 because velocity is negative. Okay? At 4 seconds, is the acceleration positive or negative? So remember, again, acceleration is the derivative of velocity. And another way, the way you see derivative on a graph is slope. So if I look at 4 seconds, that slope is definitely negative, okay? So I would say the acceleration is negative because, and you could actually compute the slope of that line. If you look, it's down 12, let's see, this is up, so if I go down 12 over 2, so that would be a slope of negative 6 because v prime of 4 equals negative 6. What is the average acceleration? So again, average acceleration is going to be the slope of the velocity from 2 to 4. So I need the values at 2 and I need the values at 4. So we said 4 was about 6, and if we look at 2, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2 is 9. So we just do slope. So 6 minus 9 over 4 minus 2 would give me negative 3 over 2. And it said, so I showed my computations, and then I just need to add my units of measure. So velocity was feet per second, if you look back up top. So acceleration would be feet per second squared. Is there a guaranteed time such that v prime of t, well, that's a typo, that t should be, it should look like this, equals negative 3/2 feet per second? Justify your answer. So if you'll go back up top, look at this velocity graph. Is this velocity graph going to be differentiable everywhere? And so basically, are there any holes, jumps, asymptotes, or sharp corners or vertical tangents? So if you'll notice, here and here, we have a sharp corner. Okay, we have a sharp corner at 3 and at 6, which means our velocity is not differentiable everywhere. So we cannot apply MVT or IVT. So we can say no, V of t is not differentiable at times 3 and 6. So, and in this case, it would actually be MVT because we're looking at the derivative of V prime, derivative of velocity. So MVT doesn't apply. So we're not guaranteed to hit that value. We may, but we don't have to. We don't know if we're going to or not, okay? So then F says, at what time t is the particle farthest to the right? Okay, so in other words, they're asking us for an absolute maximum. Right would be a maximum. Farthest to the left would be a minimum, okay? So we got to kind of deal with the area. If we go back up here and look at this graph, first of all, if you look at your critical points right here, you know you're going to have a maximum, a local max, at 5, okay? And remember, absolutes, you have to compare endpoints and critical points. So we have to compare the position at 5 to the positions at the starting time 0 and the positions at the starting time 9, okay? So we need x of 0, x of 5, and x of 9, okay? Okay, so if we go back up top and we look at the areas, I'm just going to kind of break this up into rectangles and triangles. We can compute the areas, right? So down here we have an area of 9. This is 3 by 1, 2, 3, 4, 5, 6, 7, 8. No, 9. Let me count that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 by 9 is 27. Half of that is 13.5. Okay. And then this triangle is 2 by 12, which would be an area of 12. So altogether, that's a positive area of what? 34.5? Hopefully I did my math right. If I didn't, you can let me know. This triangle is 1 by negative 6, so that would be an area of negative 3. And then here we have an area of what? Negative 18. So altogether, we go back down 21. So they didn't actually tell us where the particle starts on the x-axis. That's okay. We don't really need to know that. So x of 0 starts somewhere. I don't know. Let's just call it A. And then we know to get to x of 5, we're going to go up 34.5. And then to get to 9, we're going to go back down 21. So which one has to be the greatest value? Well, it has to be x of 5. We're going up, or to the right, sorry, we're not going up, we're going to the right. We're going to the right more than we're going to the left. So x of 5 has to be the farthest to the right that you're going to be. You have more positive area than you have negative area, okay? So you can just explain it some like that. So x of 5 is the absolute max, or is the time, at what time? So careful, we should say at 5, at time 5. The particle is farthest to the right. Because before 5 is more positive area than the negative area after 5. Okay? So leave that up for a second so you can get that written down. And then we'll look, and we have one more example, which is a function. They give us an equation. Okay, so let's look at example 3. So this says a particle moves along the x-axis so that at time t, its position is given by this equation. So we have a position equation. So the first thing we want to know is it moving to the right or the left? So direction always comes from velocity. So the first thing we should do is take the derivative of our position, which would give us 3t squared minus 12t plus 9. And so we need to know at time 0 what is the velocity. So we're going to plug in 0, which would just give us 9. So because it's positive, we're going to move to the right. So we're moving to the right because velocity is 9, which is positive. Okay, at time 1, is the velocity increasing or decreasing? Okay, so if the velocity is going to be increasing or decreasing, we need to look at if the acceleration is positive or negative. So we need the second derivative. So we need to take the derivative again, which would give me 6t minus 12. So at 1, what is the acceleration? If I plug in a 1, I get 6 minus 12, which is negative 6. So I'm going to be decreasing because the acceleration, that should be a 1 right there. A of 1 is negative. Okay, and then it says find all the values of t for which the particle is moving to the left. So basically, where is the derivative negative? So we're going to do this just like we did with critical points in the number line. So we're going to set our derivative equal to 0, and we're going to solve. You'll notice the first thing you could do is factor a 3 out of all of these. Always look for your GCF. And then just factors of 3 that add up to negative 4 would be negative 1 and negative 3. So we get t equals 1 and t equals 3. So we're going to put them on a number line. And we should always start it at time 0 because we're not going to have negative time. So if you remember, pick a number less than 1, greater than 1, and greater than 3. So we're going to pick maybe a half, and 2, and 4. So if I plug a half in here, a half minus 1 would be negative, a half minus 3 would be negative, so a negative times a negative is a positive. If I plug a 2 in, 2 minus 1 is negative, 2 minus 1 is positive, 2 minus 3 is negative. A negative times a positive is a negative. And then if I plug a 4 in, 4 minus 1 is positive, 4 minus 3 is positive, so positive, positive makes positive. So where is the particle moving to the left? From 1 to 3. So you need to write it in interval notation, 1 to 3. Okay, so that's particle motion on the x-axis.